Hey guys, in this video we're going to be covering what was covered in last night's review for the first midterm. If you're not a UCF student in CDA 3103, then this video might not make much sense because we're going to be following review that is for our specific exam. But if you are a student in CDA 3103, go ahead and go to the description of this video and you'll find the link to the Google document that I'm following. I had made a practice review for those of you, or sorry, a practice exam for those of you who weren't at the review, and I'm just going to be going off of that document. I'm not going to do the entire thing since I've made some videos that cover some of the topics that are on the practice exam, and I'll just go ahead and link to those when they come about. But the first thing we're going to go over is problem set 1, which is binary conversions with integers. So for number 1 from this set, we're given that a equals the value 1010, 0110. And with this number, we're asked to convert it to first an unsigned value, which is a, so I'm just going to write a for unsigned. And we're asked to convert it to a 2's complement value. And that was a little bit of a bad way to put it. So what I meant by this was, for an unsigned value, we're going to say that this binary number is being represented as an unsigned number. So we're going to be converting it to decimal in such a way that we're going to treat it as an unsigned number here, and we're going to be treating it as a 2's complement number here. So our problem is to convert this to decimal. And this is just problem 1 from the practice exam. So to convert this as an unsigned number is extremely simple. We just have to keep in mind that this is going to be the 2 to the 0's place, the 2 to the 1's place, the 2 to the 2's, 3's, 4's, 5's, 6, and 7. So our value just ends up being 2 to the 7th plus 2 to the 5th plus 2 squared plus 2 to the 1st, which ends up being 128 plus 32 plus 4 plus 2, which equals 166. And if you're confused as to how I got the 7, the 5, the 2, and the 1, I'm just looking at the bits that are 1s. And you can see that they correspond to 7, 5, 2, and 1. I'm not sure if you can see that because it's tiny, but these 1s are in that many spaces from the right of the number. Now for 2's complement, things are a little bit more complicated. We have to take this bit sequence and we have to first do a bitwise inverse. So I'm going to do, I'm just going to write the absolute value of a, just to make it positive, is going to be 0, 1, 0, 1, 1, 0, 0, 1. And then we're going to go ahead and add 1 to that. So I'm just going to add 1, or I'm going to add 1. Ignore my scribble. And we're just going to get the same value, except there's going to be a 2 at the end now. So 1, 0, 1, 0. And now we just have to convert this value to decimal. So when we look at this, we're going to see that we're going to get 2 to the 1st, plus 2 to the 3rd, plus 2 to the 4th, plus 2 to the 6th. So we get 2 to the 6th, plus 2 to the 4th, plus 2 to the 3rd, plus 2 to the 1st, which ends up being 64 plus 16, and this is the absolute value of a, keep that in mind. We're still looking at that. 64 plus 16 plus 2 to the 3rd, which is 8, plus 2. So we end up getting 90 from that. But then we have to remember that since our sign bit up here is 1, the first bit up here is 1, we know that our answer is negative. So our actual value of a is going to be negative 90. Now, if you look on the review, or if you look on the practice exam, for number 2, I'm not going to do it on here, but we have let a equals the value 0, 0, 0, 1, 0, 1, 1, 1. And the reason that I put that in there is to demonstrate to you that this is going to have the same value for being unsigned or 2's complement. So I'll go ahead and just write the number out, but I'm not actually going to do the problem, just to save time. 0, 0, 0, 1, 0, 1, 1, 1. We could, if we were trying to convert this to decimal, if we wanted to find the unsigned value, it would be the same as the process up here. But if we wanted to convert it to decimal, if it was a 2's complement representation, you can see that it's already positive because this bit is 0. So we don't really have to do anything else. These are going to be the same value if it's unsigned or 2's complement. It doesn't really matter. Okay, so let's go ahead and move on to number 3. I'm going to put this here to save space, then we're going to do number 4 on the other side because it doesn't take up very much room. So we're asked to convert, we're going to say a is equal to 42, and that's in base 10. And we're asked to convert this to binary. And we're asked specifically to convert it to 8-bit binary. And the way that we do that is we just continuously express 42 as multiples of 2. So we're going to say 42 equals 2 times 21 plus 0. And then we're going to get 21 equals 2 times 10 plus 1. 10 equals 2 times 5 plus 0. And then we're going to get 5 equals 2 times 2 plus 1. And then finally we get 2 equals 2 times 1 plus 0. And then 1 equals 2 times 0 plus 1. And now we know that we're done, because if I go and copy the 0 over here, we're just going to get 0 equals 0 times 0 plus 0. Then we'll copy another 0 and we'll get the same thing. So we're just going to read these remainders, these 1s and 0s, from bottom to top. Now we have 42 in binary, but we have to represent it with 8 bits. So I'm going to pad it with 2 bits, and then write the rest of the number in order. 1, 0, 1, 0. Now let's go ahead and do number 4. Number 4 is a little bit trickier, because we're asked to convert the value, negative 14. And we have to keep in mind that negative 14 will have to be represented using 2's complement, specifically because it's a negative number. Unsigned representations like this, they don't afford the opportunity to represent a negative number, so we're going to have to use 2's complement. So that what we're going to do is we're going to find the positive binary representation of, the binary representation of positive 14, and then we're going to negate the binary representation under 2's complement. So let's go ahead and do 14 equals 2 times 7 plus 0, and then 7 equals 2 times 3 plus 1, 3 equals 2 times 1 plus 1, 1 equals 2 times 0 plus 1, and then we're done. So we know that 14 is going to be 1, 1, 1, 0. We're going to pad it out to 8 bits, so 0, 0, 0, 0, 1, 1, 1, 0. And then we're going to invert that and add 1. I'm going to go ahead and save space and do this all in one step. So we're going to get 1, 1, 1, 1, 0, 0, 0, 1. So it's going to become 1, 1, 1, 1, 0, 0, 1, 0. And we're done. So that's number 1, problem set 1. So there's problem set 1, that's numbers 1, 2, 3, and 4. 2 can be inferred. Let's go ahead and move on to problem 2. I'm going to clear my paper and we'll start over. Alright, for number 2, I already have a video on combinational logic, so I'm not going to go that far into it, but I'm just going to give you enough to get started on this problem. We're going to take it from the description of the problem to the truth table for the problem, and then you should be able to use all of the tools that I gave you in the other video to solve the rest of it. So we have this unique issue where we have a boogeyman in our attic, and he won't stop messing with our stuff, and we need to get rid of him. So we decide to build a boogeyman trap, and it's a combinational circuit that consists of 3 sensors. We have one sensor, which is called F, which is a fur detector, and then we have, let me just go and write that real quick, so fur detector. Then we have B, which is a boogeyman detector, so that'll fire if the boogeyman is detected. And we have W, which is a wall clock. And this will fire if the time is between 9 p.m. and 6 a.m. So now let me give you a little bit more background. You have a dog named Bacon. And Bacon likes to kind of move around the house. He's a bit of a sleepy dog though, so between the times 9 p.m. and 6 a.m., you can rest assured that he'll be sound asleep in your room, and there's no chance that he'll be in the attic. Now our fur detector can detect Bacon because Bacon has fur since he's a dog, But our fur detector can also pick up cats, it can pick up rats and mice, and it can pick up bats. And we're not really worried about those types of animals. We're not worried about vermin that live inside the attic. We're just worried about bacon. So we want to make sure that if there's any chance that bacon is in the attic while the boogeyman is in the attic, we don't set off the trap, because then we'll end up hurting bacon and we don't want that. So to do this, even though it sounds complicated, we can just set up a truth table and it'll make things much simpler. So let's go ahead and do our inputs, which are going to be F, B, and W, and then our output is going to be T, which is going to set off our trap. We have 3 inputs, and 2 to the third is 8, so go ahead and make enough room for 8 inputs. So there's 4, and there's 8. Now go ahead and write out 0 to 7 in binary, so I'm just going to enumerate those values. So 0, 0, 0, 0, 0, 1, 0, 1, 0. And I'd highly recommend that you memorize the values 0 through 7. You don't have to, you can always do it sequentially, or you can do it just by thinking about it. But you're going to be working with values between 0 and 15 for basically the rest of your computer science career, especially when you get into hexadecimal values. It'll come in extreme handy to have this, so I just recommend memorizing it. Now, let's go ahead and get back to the problem. So we know, first of all, that if the boogeyman is not in the attic, we're not going to set off the trap, because why would we? It'd be a waste of energy. The boogeyman is not there if the boogeyman detector, forgot to write detector, if the boogeyman detector doesn't say he's there. So when the boogeyman detector is giving us false as a value, we can be assured that we're not going to set off the trap. So we'll set those to zeros, all of these regions where the boogeyman detector is saying that he's not there. Now we have to consider the other cases where the boogeyman is in the attic. So we've now eliminated the possibility that the boogeyman is not in the attic. So if we look at these 2 cases right here, we see that there's no fur detected in the attic at all, which means that there's no cats or rats or bats or anything in the attic, but there's also guaranteed to not be bacon, since bacon would have been picked up by the fur detector. And that happens regardless, or that's true regardless of whether bacon is guaranteed to be in your room or not. So if there's no fur, and we have the boogeyman, we're going to trap him. So we're going to set those both to 1. And now we just have these 2 cases, which are a little bit more complicated, where we have the boogeyman in the attic, and we also are detecting fur in both of these cases. So in this case, the time is not between 9 p.m. and 6 a.m., because remember, our wall clock will be true if the time is between 9 p.m. and 6 a.m. Now, since the time is not between 9 p.m. and 6 a.m. and there is fur in the attic, there's a possibility that the fur in the attic is coming from bacon, so we're not going to set off our trap. Now, in the next case, to the contrary, bacon is sound asleep in our room. The time is between 9 p.m. and 6 a.m., so we know that bacon is sleeping in his little dog bed, and he's not in the attic. So we detect fur, but we're not concerned about the animals that are in there. We just want to trap the boogeyman, so we're going to set off our trap. And there's our truth table. Now if you go ahead and you click on the link that's going to show up right here, you can see my video on combinational logic and then finish up this problem using this truth table. And that should be enough to get you started. Now for problem 3, we have a ripple carry adder. And I would love to do a video on this, but it would be a little bit unnecessary because the operation of a ripple carry adder is pretty easy to wrap your head around. It's just a series of adders stacked together. So instead, to save some time, I'm just going to link you guys to the appropriate slide. If you go ahead and check the link in the description, you'll get a link to web courses. Make sure you're signed into web courses before you view this link. If any of you actually need an interactive, or not interactive, but an actual walkthrough of how to do the adder, just come to office hours and I can do it on the board. I'm not going to waste time in the video to go over something that's this simple. Now similarly for problem 4, I already have videos for both of those, so if you look at number 1, there's a video to convert an IEEE 754 single precision floating point number to decimal, and there's also a video to take a decimal number and convert it back into IEEE 754. So go ahead and look at my channel. I think it's called How to IEEE 754. You can look at both of those, and they'll show you exactly what to do. And what's cool is that for number 2 in the example that I gave, you don't get a repeating mantissa, but in the video that I do, you do. And I cover both cases in the video anyway, so we'll be good to go on that front. Now, problem 5 is the one that I'm going to cover. So if we look at problem 5, so it's a pretty unique problem. We're given these two values. The first one is x, which is 0, 0, 1, 0, and then 1, 0, 1, 0, and y, which is 0, 0, 0, 1, 0, 0, 0, 1. And we're told to perform a set on less than operation on this 8-bit ALU. So if we look at the inputs and outputs of a traditional ALU, which is going to be a 32-bit ALU, I'll draw the typical block diagram shape for an ALU. There's our op, and then we have x going in here, we have y going in here, we have result as one of our outputs, we have 0 as one of our outputs, and we have overflow, and then we have carry out. Now for the 32-bit ALU, x is going to be 32 bits, y is going to be 32 bits, and result is going to be 32 bits. Operation is going to be, for the purpose of this class, just assume that it's a variable number of bits, and it can be, it's probably going to be no more than 4 or 5 for any real ALU. But it's just going to tell the ALU what we're going to do with these two numbers. So the ALU can add x and y, it can subtract x and y, it can do a bitwise and, a bitwise or, it can find the inverses of either number. It can do many things, but what we're going to do is determine if x is less than y, which is an operation called set on less than in the MIPS architecture, which this class is based on. So the way that the computer does a less than determination is it will take, remember we're determining if x is less than y. Now if we subtract y from both sides, we get x is less than, x minus y is less than 0. So what the computer will actually do is it's going to subtract y from x, which is something it can already do. And remember that the way that computers do subtraction is they just add the negative, so we're going to do x plus negative y is less than 0. So the first thing we have to do is we have to find negative y. So up here, and I know that this is kind of sloppy looking, but I'm going to add a line, because lines are great. So we're going to invert this value, so we're going to get 1, 1, 1, 0, 1, 1, 1, and we go to get a 0, but we're going to add 1, so there's negative y under 2's complement. So now all we have to do, I'm going to copy x, 0, 0, 1, 0, 1, 0, 1, 0, and then I'm going to copy negative y, 1, 1, 1, 0, 1, 1, 1, 1. I'm going to add them because the second one is negated, so it's the same as a subtraction. And now I'm just going to do an addition. So I'm going to do 1, then I'm going to get a 0, carry the 1, 0, carry the 1, 1, carry the 1, 1, 0, carry the 1, 0, carry the 1, 0, carry the 1. Now we have this carry out of 1 here, but if you remember from how arithmetic works, if the two carryouts are the same, the carry into this most significant bit here and the carry out of the most significant bit, there was no overflow, so that's really good. We know that our carry out was 1, and if you remember, two of our values that we had to specify were overflow and carry out. So right off the bat, we can go ahead, I'm going to leave some room to write other values here. We can say that overflow is false, our answer is correct, and we know that carry out was 1. So one thing I'd really like to point out here is that carry out was 1 but overflow is false. A lot of people will sometimes conflate carry out with overflow and think that they're somehow correlated. When we're doing signed arithmetic, and none of what I'm about to say applies to unsigned arithmetic. In unsigned arithmetic, carry out and overflow are the same thing. But in signed arithmetic, carry out alone doesn't say whether or not there was overflow. You have to compare these two bits. So if you only know the carry out of the most significant bit, you can't say anything about whether there was overflow in the operation. It's just meaningless without both of these bits being represented. Now if we look at our result, if we subtract x from y, and we know that our value is 0 or greater because our sign bit is 0, if x minus y is greater than or equal to 0, we know that x must have been larger than y. So like imagine a number line in your head, in case you're having a hard time visualizing this. If you're not, try not to laugh. If you imagine a number line in your head, this is 0. And if we move along this number line, and we have a pretty big value of x, and then we have a larger number for y, going backwards, if we end up at a value that's less than 0, we can see that this is less than 0, then we know that x must be less than y. But in this case, since our sign bit was 0 here, we know that this number is 0 or positive, which means that x was not less than y. And it's tempting to look at this result register, or this result output bus. It's tempting to just take this result and stick it in there, because we know that this result register is going to be 8 bits wide. This is the diagram for a 32-bit ALU, but our ALU is 8 bits wide because our input values are 8 bits wide. Keep that in mind. What we actually get is we get a Boolean value represented using 8 bits. So set on less than, it's just asking if x is less than y. That's a yes or no question, so it could be represented using only 1 bit, but we wanted to reuse this result output. So what we ended up doing is we just specify 1 or 0 to be an 8-bit number in this case. So if we look at our result, x was not less than y, so our result is not just going to equal 0, it's going to equal 8 zeros. So essentially, this bit right here, this sign bit, just gets copied right into this bit spot, and the rest of these are always going to be zeros. These first 7 bits, or the first 31 bits in a 32-bit ALU, or the first 15 bits in a 16-bit ALU. These are all going to be zeros, and the sign bit just gets copied, because if this value were negative, we would know that x must have been less than y. So our sign bit would have been 1, since all negative numbers have a sign bit of 1. We would put this in here. Our result would be 1, which would mean that x minus y, or x is less than y, would be true. Now we do have one more output, and a lot of people get confused by this. It's the 0 output of the ALU. And this is usually used in equality checks, where we'll subtract one number from another, and if the result was 0, we know those two numbers were the same. That's how comparisons are done in the ALU for equality. We're doing less than, and what we're going to check is we're going to check this result, but in reality it wouldn't matter which result we checked. I guess it would. We're going to check this result though. We're going to check this result. I was circling the wrong one. We're going to check the final result of our computation, and since this result was 0, we know that 0 is going to be asserted. So since these are all zeros, we're going to go ahead and say that 0 is 1. Now if you attended the review yesterday, I actually made a mistake here and I used this result. I'm pretty sure, I'm having a hard time remembering, but I'm pretty sure I used this result, and I said that it wasn't equal to 0. The way that the 0 output works is it takes all of your result bits and runs them through a NOR gate. So in this case, 0, NOR 0, NOR 0, NOR 0, NOR 0, and so on would just be 1. And that's number 5 done. Now, the next problem is number 6, which is a Booth's algorithm problem. And I already have a video on Booth's algorithm, so just go ahead and click here if you want to learn about it. That's the end of this video because Booth's algorithm is the last problem on the practice exam. If any of you have any questions, go ahead and shoot me a web course message, or you can also message Mariah. Mariah is going to be having her review next Tuesday, so go ahead and check your web courses announcements for details on that. Thanks for watching.